Drilling fluids touch just about everything in the drilling process. We're here to deconstruct the drilling process and drilling fluid concepts to provide a deeper understanding of our industry. In each episode, we'll share information, talk to interesting people, and maybe share a few stories along the way. Welcome to the Flowline, a production of AES Drilling Fluids, brought to you by Matt Offenbacher and Justin Gauthier.
All right, everybody, welcome back to another exciting and extravagant episode of the Flowline. We've got a good one today. But first and foremost, Matt, hate to bring the A word into this conversation, but the Astros are not in the race.
No.
For the World Series this year, are they?
No, and I mean, frankly, I think if I was being honest with myself, they weren't in the race a long time ago. But there was always the possibility, right? You know, but you're saying there's a chance.
Yeah.
And so it's kind of weird. I feel like, you never want it to end, but there's always next year. And for the first time in a long time, I'm not physically and emotionally unavailable to my family in October.
Right.
So
big
there's
win
that.
for the Offenbacher family.
Yeah, I think some people will appreciate a kinder, gentler Matt for at least an extra month every year. So
Nice.
Yeah, no, it's tough to see the way they kind of fizzled out, but a lot of injuries, a lot of other stuff.
Yeah.
And next year.
Okay. Well, if we're not going to talk about the Astros, then I guess we can either move on or, well, I guess in the baseball world, my son's team is 2-2.
Yeah.
The old doubleheader league. They're the Houston Wildcatters. It's a well-known organization around Houston, and of course it's the Wildcatters. And the logo is a derrick with a bat and a ball and oil splashing out.
Sweet.
Yeah. So which is interesting because they've got teams all over Texas. They're in California, and apparently the Dodgers have reached out to them for some collaboration. And one of the directors was telling us at a big event that they had not long ago, and I was like, wow, that'd be interesting. California getting involved with the Houston Wildcatters, just kind of ironic, right? Considering the anti-oil and gas, but
Yeah.
Nonetheless, they're 2-2. They got a big tournament coming up this weekend, and the boys are pumped.
All right.
My daughter's softball team won their first. They had a tournament last week, and their first one of the fall, and they went 7-0.
Wow.
Yeah, it was good.
I was gonna say that's getting it all together.
Yeah. We entered the season into a C-class tournament, which is like typically like a starter team, and so just kind of see where we stand. And
You stand pretty well, is what it sounds like.
yeah. They told us we can't enter C-class tournaments anymore because it was a little unfair for everyone else.
Aw.
But it was cool.
Okay.
And so it's we're full mode right now, so it's been fun. And
Okay.
so maybe we'll give updates on the baseball and softball world for a little bit instead of the Astros until they come back, or we could talk about the Texans. But I don't know much. I haven't been really to watch football, and I don't know if you watch. Are you watching football?
Not some, but not really.
Okay.
I mean, my son actually loves watching football. My oldest,
yeah.
and
Very cool.
He sort of keeps track of it. And his school, there's some people affiliated with the organization who. So like he.
Mm-hmm.
Anyways, it's sort of a. I would say I feel obligated to keep better track now, and I really want to take him to a game this year.
Yeah.
So
Very good.
hopefully I'll get my act together and get on that. But
Right.
it's been tough sledding for them. Hopefully, but we've never had expectations for them because every time we get our hopes up,
Yeah.
it ends in misery. So, there's
It
that.
does. Is he interested in even flag football? Is he into wanting to play, or is he just enjoying observing?
I think he just likes watching the games. I mean, he's very much he's playing soccer now. We did t-ball last year.
Yeah.
He's very much a anywhere the wind blows kind of kid, it seems.
But he seems like when the times I've seen him, he seems like a high energy type kid to where I feel like he would do well in environments like that.
Yes, well, he wants to run. He just doesn't want to run like under any constraints. Like
Football might be good.
we were at a high school basketball game, and during halftime he goes, "Dad, can I do run around the arena?" And I was like, I mean, I guess if you want. And so he just goes down to the bottom of the bleachers and just starts running. and does like a full lap all the way around. And, like, there's other people doing things, kind of like, hey, watch out,
Yeah.
And he just comes back.
Zigging
like,
and zagging through the
and he's
crowd.
like, thank you. It was like, okay.
He's got some energy pent up that he needs to release.
I think soccer is
that's
a good chance, but, like, I think once again, he needs to learn that there's a ball that you're supposed to get involved with. So
I'm just going to run.
Yeah.
That's great. Well, hey, look, that's all in good fun. But anyway, the Texans, I think they're, I don't know, what are they, 1-3 or something?
Something like that.
Yeah. Anyway, clearly I haven't been paying attention. But last thing I'll say on the sports side, this weekend, when this drops, this will have already played, but the U of H plays Texas Tech, which is a big deal, I would say, in Houston sports world coming up. That's probably one of the bigger ones. So,
yes, and it's cool to get excited about that.
Yeah, I mean, if Houston somehow pulls this off, it'll be good for everyone, especially U of H. I mean, they've been decent, and that would kind of, I feel like, put them on the map a little bit more. So that'd be fun.
Yes, although we have a substantial listener base that are Texas Tech alums or fans,
right,
and we respect and appreciate your fine institution.
Yes, that too. I don't know. I have no. I mean, again, I'm being from Canada, I don't really care. And doing grad school, University of Colorado, I should be a Buffs fan, but I think I've watched maybe one game. So anyway, I digress. Nonetheless, let's talk drilling fluids. I think we've done our close to 8-minute banter at 6. But some of the best episodes come from listeners, and of course conversations that you may have at Mud School. But it sounds like we had a gentleman who finished Mud School, and you asked him the question, what was the hardest part? And he proceeded to tell you about clay chemistry. And so good conversation.
I mean, congrats. We're not going to throw out your name there just out of respect for your own privacy, but thank you for the message. And, you inspired our episode to talk about Mud Schools in the first place. And so when you sent me the message that you graduated, that's exciting. And the other part of it, you said, I was real curious what you found to be the hardest part. And you said, well, clay chemistry was tough. And I was like, you know what? We got to do a podcast today. What if we go through this, which honestly, it's a pretty visually driven thing, so we'll see how this goes, but at the very least we'll try and do a little primer and help people think through clays and sort of why they behave the way they do, and who knows, maybe it'll inspire some other listener questions and we can dig into that too. And
at the very least, just kind of a refresher and kind of blow the dust off a topic that you learn in Mud School, but it's not like you're running around a drilling rig talking about clay chemistry, right?
No.
So it'll be a good refresher for me, even personally. I haven't talked about this in a while, but that said, let's get this thing going. So Matt, how would you firstly describe what clay chemistry is, just broadly speaking?
So there's a lot of different clay minerals, and there's a lot of arguments to be had about which one is which. But when you break down categories, the main area we need to talk about when we're talking about how a lot of the materials we use are going to be silicates. And even that's broken into a couple of categories, and one that we're not going to go into much of detail on are called chain silicates. These would be like attapulgite and sepulite. You're sort of like needle-shaped. They don't interact a ton with water. They like salt gel, right? Like it shears and yields, but it's not actually hydrating per se. The ones we want to talk about with water interaction and a lot of the things that we drill through that give us a hard time would be called layer silicates. So examples. You may have heard these before: kaolinite, smectite, illite, chlorite, mica. And so, believe it or not, they're special because they are composed of layers.
Yes.
That's why they're called layer silicates. And in essence, you've got basically two different types of layers, and one is silica. So think of a pyramid, a tetrahedron. It's got oxygens on the outside and then silicon on the inside. Or you have an octahedron. That means an eight-sided shaped thing. And it's got hydroxyls, OHs around it, with aluminum or magnesium inside. And basically the patterns of how the silicate and the aluminum or magnesium layers, how they're stacked, sort of tells you what they're made of and how they behave. So then we got to break it down by the ratio, the layers that we get.
Okay.
And stay with me here for a minute. And I think as we get through this, you'll start to understand how these interactions with water and things happen. But so you have those silicon and aluminum magnesium layers, and the ratio. So for example, if I have one silicon, one aluminum, magnesium, like repeating. That's called a 1-to-1, right? Because I have one layer to one. So that would be like kaolinite, a 2-to-1. So 2 silica layers, and you got an aluminum magnesium layer in like sandwiched in between. That would be like smectite or illite. And then and remember smectite. I don't want to get too far ahead of us. That's a really like water sensitive clay, right? That sandwich part will sort of be relevant. And then chlorite, which is another material that we drill through. Depending on who you want to argue with, it's a 2-to-2 or 2-to-1 layer, because what it has, it has the sort of silica, aluminum, silica like sandwich, and then it has another layer of magnesium hydroxide or brucite. And so that sort of sandwich is repeating. So anyways, you've got those layers, and then what happens is, depending on the material, you can have these shifts in charges. And this is where we start getting things where things get attracted to one another.
And that's where, in the drilling fluid space, that's where we really start to see things happen.
Yeah, I mean, this is where when we get into inhibition, you'll say, oh, okay, I understand how these products work a little bit more because of the charges on the clays. Hopefully.
Right. Okay. Well, let's kind of dive into the charges piece then.
Yes. So let's say I've got an aluminum layer, and I swap one of those aluminum, so Al3+, for magnesium. Well, what happens is that's Mg2+. So I've got an extra electron. So now I've got a negative charge. It could be that those hydroxyls I mentioned are on the outside. At a low pH, they lose a hydrogen, and so they're leaving O-. So I've got negative spaces, right? So on these negative surfaces of a clay layer, it creates potential for cation exchange, which, remember, we measure that cation exchange capacity on our MBT test.
Yeah.
So if I got a -1, I might, let's say, for example, pick up a sodium. So there's a sodium sitting there. And think about this happening over like tons and tons of surface area over and over again. But what ultimately happens is, on the edges, I've got those silica on the or aluminum at the edge, so that's positive, like Si4+, Al3+. Inside, on the surface, think of like, once again, a plate or something, very like edges versus surface. Edges positive, surface negative. So the surface is where I can pick up these other cations because I have these negative charges. So if I have a high cation exchange capacity, lots of negative places on the plate, it implies more water interaction. And in essence, that is because water is very polar. So it's got an area where it can stick. The other thing you have to keep in mind is, just by the size and nature of these clays, like smectite and illite have much higher surface areas, so more areas for water to stick to it.
Right.
Kaolite and chlorite not as much. I'm getting ahead of myself. Sorry. But anyways, this is where these cations can exchange. So you think about sodium. Well, for example, we've talked about this in the past. The sodium ion, that radius is big enough that water can get in there, and basically want to stick, and that will cause these clay layers to separate.
Which would then increase viscosity?
It could increase viscosity because they're interacting. We could be swelling. Sometimes they break apart entirely. But it allows that water to fit in and also expand and create that space.
Got it. Okay.
Now, let's pretend I was going to, this is where potassium, for example, if I can swap that potassium for sodium, the layers get closer together because potassium has a smaller ionic radius, too small for water to fit in, and now I've got some inhibition.
Right. Okay.
The other thing is low pH. So at low pH, those hydroxyls on that outer layer lose a hydrogen, and so that leaves like an O, or it leaves an O-. You got these H pluses floating around, so it's more acidic. This is why when clays are, when we drill surface, we normally don't want a really high pH because all that gumbo-y stuff we're drilling through.
Yeah.
It's because basically we're neutralizing that, and that will cause the clay to break apart. So pH can have an effect on that kind of thing, water sensitivity. So in essence, water leads to expansion, and this just causes swelling. Some clay layers don't have any exchangeable cations. So smectite has a ton. That's why we always talk about how reactive it is, right? Something that may be less water sensitive, like kaolinite, it has no exchangeable cations. Chlorite only has that magnesium hydroxide, or AKA the brucite layer, and then illite, the only exchangeable cation is potassium. So water doesn't really want to get in there as well. But I think the reality is, from a water sensitivity perspective, we're talking about these pure states, like pure Montmorillonite, pure smectite, pure illite, right? A lot of our stuff is mixed together, which means you can study these rules as well as you want, but the mechanism is probably going to be present to some degree no matter where you're drilling.
Right.
Like, you might not have a lot of smectite, but it's there, but it may be mixed with some other things. And so that may affect your drilling, it may not. And this is why we ultimately, instead of just like, oh, you got a lot of smectite there, it's like, okay, well, let's test how it responds to an additive, instead of just being like, oh, just add this stuff then.
Right.
Because the behavior is going to change when you've got a combination of things.
Right, which, downhole, you're always getting kind of a blend of a lot of different stuff.
Exactly. And so, I mean, water sensitivity is one thing. Sometimes these things can, become brittle and break apart or disperse. But what we're trying to do when we have exchangeable cations, when we can offer some inhibition because we have those in our clay layer, I mentioned we're trying to either shrink the space by providing a different exchangeable cation. So swap sodium for potassium is a very common one. There's other additives, other salts. Calcium is another one that has a smaller ionic radius that it is tight enough that water can't fit between the layers, and so that helps us provide some inhibition. Another one we talk about is anionic polymers like PHPA. We use that all the time, right? And it works pretty great for a lot of inhibition.
Mm-hmm.
What is it? It's an anionic polymer. And what that means is it's got a negative charge. Remember how you mentioned the edges of clays are positively charged?
Right.
So that stuff wants to stick all over the sides of that clay and basically create a very thin film barrier that water can't pass through.
Okay.
So instead of getting the clay layers tight together, what we're doing is we're just covering up the edges.
Gotcha.
And then like an amine. So amines are cationic, which means they go in and they stick. But amines have a bunch of sites. It's not just one potassium ion.
Yeah.
They got a bunch of stuff that wants to stick to everything, and that's why they work as really good shale inhibitors. Is they'll stick all over and draw that clay platelet together. Mm. So think of a longer chain than just one ion. Other things that we've talked about in other podcasts, things like glycols, where they create these little micelles and they plug the edges and absorb to other surfaces, limiting water entry. And then silicates, the other one that's worth mentioning is when you know your clay is natively acidic, running something that's very high pH, and when it encounters an acidic region, it precipitates into calcium or magnesium silicate and forms a solid, so blocking water entry. That precipitate is sort of forming your inhibition mechanism.
Okay.
So a lot of different ways that can work, and a lot of those things you work together. Like you'd have some potassium, but you might also add a cationic polymer or an amine.
Right.
So anyways, like, hopefully my goal here, as abstract as that may have come across, was to try and link the nature of these charges with how they interact with water and how we can stop it.
Right.
How'd I do?
Yeah. No, I think went very well. And when
Okay.
you look at, and it kind of take it one step further, is in the product development and understanding how to, if you do have, like, clay chemistry is one thing, is the simple is, we have a bag of gel and you add water and here's how it's happening and here's how it's increasing viscosity. But a lot of this is important to understand how to do either fluid design or product design, which inhibitor to use. And so that's where, when you try and tie it into the real world, outside the lab, I think of that, like, would you say you guys spend a lot of time understanding the clay chemistry to design different products or when to select different inhibition packages?
Absolutely.
Okay.
And so, for example, we've encountered, we've been running all this X-ray diffraction, and you can do a secondary step called a clay slide, and you get detailed information on exactly what type of clay you're drilling through and that sort of thing. But we're looking at those relationships to help make sure we're recommending the best fluid for an area.
Right.
And, sometimes you will see something there where it's just like not going to work. Where, okay, we're having whole problems. We think it's the clay, but it's like, oh, wait, there's a bunch of salt in that formation. Like,
right.
It's actually dispersing. It's not reactive and washing out. It's just soluble. And so we're able to come up with different fluid formulations, or at least understand that if you go down the wrong path, you could spend a lot of money and still not solve the problem.
Right.
So, yes, and I think, from sort of the like boutique perspective, a lot of this comes down to even where you are. Like, we're sort of geolocating some of our understanding of clay mineralogy across, Oklahoma, where everything's just crazy weird. You have formations folded on top of each other, or the Gulf Coast, or some of those areas, the Haynesville. Yeah. But like the Permian, it's pretty well, like we sort of, like we don't have a bunch of people asking us for a bunch of inhibitive materials there, right?
Yeah.
The formations are pretty well known. We can drill through them. We get it. But if we see something unexpected, we know that too. So
Got it.
Yes, understanding this is important both for troubleshooting and a lot of times what not to do.
Got it.
So yeah.
Okay. No, that helps tie it up, and kind of like bridge the gap between, the chemistry side and the theory, and then into the, what one might be able to connect the dots with what we see in the field.
Yeah.
And then so talk really just kind of briefly about oil-based mud. I mean, does clay chemistry apply in the oil-based mud world?
It does in the classic water phase salinity story. And in essence, what you see is that, well, oil-based mud is oil continuous. That membrane, or the brine droplets that you have in there, water can move, and it's going to go to the highest salinity region. So you may have sticky cuttings or something like that when water's moving into the formation, and you need to adjust your salinity. Or you may see, embrittlement, as we've discussed. And so the water can get to the clay. It's generally manageable and quick to identify if it's happening. And so many times it's sort of not the issue. But at the same time, it could be, and it's worth recognizing that we spent all this time talking about clay interactions. Well, you may actually see it with the water phase of oil-based mud if you're not careful. So
okay, no,
yeah.
that makes sense. And then there you have it. I mean, a good 15-minute rundown of clay chemistry. I'm sure you probably spent a little more time than that in mud school on it, but I think we hit the high notes. And of course, if anyone has any questions, or if the listener who's sort of asked us a couple questions already about this stuff wants to dive deeper, heck, I'm sure we could do a full episode on just inhibition or just water sensitivity charges.
Yeah.
But again, it's as you can tell, it gets pretty in the weeds, and so but happy to do so if anyone has any questions.
Yes, but we also recognize that many of you listen to these podcasts driving home from your days off, and we want you to stay awake for that whole time. So
right.
We'll do our best.
Yeah, exactly. And with that being said, always appreciate you listening, subscribing. Just the feedback has always been great. Any questions, please reach out to Matt and I over LinkedIn, or you can reach us at the Flowline podcast at aesfluids.com. Connect with the AES Fluids page. We've had some great, just content continues to get poured out. We just released one on Tenaha, a video. Some of our, kind of comical commercials that send the message about allowing engineers to sleep at night and giving their time back is a good chuckle. But that being said, folks, appreciate it. Drive safe if you're out there on the road. And until next time, cheers.
Take care.
Thanks for listening. Please tune in next week for another exciting episode of The Flowline. And remember, may your returns always be full and your trips always smooth. Views expressed in this program belong to participants and not their employees. The program is for informational purposes only and cannot take the place of seeking professional advice. Copyright AES Drilling Fluids.